Thank you very much, Marc, for your presentation. I think we will just move on before we take audience questions. Then we will just have move on to our commentator, Steve Furber. I will just transfer presentation rights. Yes, okay. You're good to go. Yes, please. Yes.
I'm presenting, but I don't have any slides. So if people can see me, I can't actually see myself in the picture. Should I be able
we can see you. We can see you fine. Thank you.
You can all see me, but I can't. Okay. That's fine. So where to start on this? The sort of theme for this particular session was cognitive computing and machine learning. And I think one can have a sensible discussion about both of those topics without worrying at all about issues of machine consciousness. But I think in order to address the speaker's talk, then I think we need to start in a slightly different position. So I remain firmly of the view that consciousness is actually still way beyond anything we can sensibly talk about when it comes to machine intelligence or machine systems. We don't know where consciousness comes from. We don't know how to test for it. I've spoken to a number of people, and I understand that the sort of feeling I had when I was quite young was wondering whether everybody in the world apart from me was a robot. This is fairly common thought for children to go through, and as we get older we realize by sort of applying principles of symmetry and properties of extrapolation that the most likely explanation of the world is that other people are like us, and other people experience consciousness in very much the same way we do. But we have no good test for that. One of the interesting questions that I think about is consciousness applicable to all living things? Are there scales of consciousness? And in the context of the speaker's presentation and the small robots, how conscious is a slug in the first instance? I think there are reasons for viewing consciousness as being sort of hierarchical. I'm not a dog owner, but I think most dog owners would be strongly of the view that their dog is conscious, but perhaps accepting that their dog's consciousness has somewhat less scope than that of a human. So dogs perhaps are less aware of the future and perhaps even a bit less aware of the past, but very much aware of the present in terms of their consciousness. And as you go down the scale of animals, then it's easy to believe, but very hard to prove, that the scope of consciousness diminishes. I've no idea how much is diminished by the time you get to a slug. But I find it possible when looking at insects, looking at a fly bashing its head against a glass window repeatedly, to view that what I'm observing is the behavior of an automaton, rather than the behavior of a conscious being. These are all very hard problems. Now, when it comes to running models on a computer, I think one has to distinguish between the model and the computer. And firstly, the sort of computers that we use to support models of brains are not adequately described as finite state automata. They have quite a large number of non-deterministic internal behaviors, which take them outside that rather rigid description. I'm not sure that matters very much. But when it comes to computers modeling neural networks, which biologically might be responsible for generating consciousness, then it's an unanswerable question at the moment as to whether that model would display the same conscious behaviors as the neural network. This is a common analogy is a flight simulator. Is a remarkably accurate way of predicting how an aeroplane will behave. It's even a very effective way of training pilots, to the extent that I understand that airline pilots that do type conversion do all their training on a simulator, and the first time they fly the new type, it's fully loaded with passengers. Is the simulator flying? Well, the computer clearly isn't flying. Is the model flying? In some kind of physical sense, yes. And I think one can extend that analogy to models of biological neural systems. I would certainly never assert that the machine is conscious. I might, under the right test conditions, be convinced that the model was conscious. And I think we can actually say the same about biology, that the brain as an assembly of neurons is not conscious, but the brain generates models, and those models display consciousness. So I think there's a distinction between the machine and the model that the machine supports. And just as a computer is very capable of supporting models of flying, it's probable that it's capable of supporting models of consciousness. Now, I say probable because we still don't know what consciousness is. It's generally accepted by most neuroscientists I talk to that consciousness is an emergent property of large and complex neural systems, but of course this isn't proven or well established. I think the reason why it's generally accepted that that is the case is because it's very hard to answer the question, well, if it isn't that, what is it? And of course there are attempts to describe explanations for consciousness that go beyond sort of physical neurons, sort of description you find in Roger Penrose's Emperor's New Mind book, which again actually uses an argument based on Turing machines to argue that no Turing machine is capable of displaying the full capabilities of the human brain. I think for reasons that I've outlined previously, I view that argument as flawed, as unconvincing, because the models that we run on our computers are not Turing machines. They're non-deterministic. They don't, if you run them twice, they don't give the same behavior. One has to accept that until we can build models that demonstrate evidence of consciousness, then we don't know whether the neural model is sufficient or whether there's something beyond that. And we are currently a very long way indeed from being able to construct such models that potentially might display consciousness. Which is why I say it's not a question that's really to the fore in the kind of work that's going on in the Human Brain Project. In the Human Brain Project, the stuff that we describe as cognitive computing is sort of machine algorithms with sensory inputs and actuator outputs, the sort of system you might want to control a driverless car or a robot vacuum cleaner. And I think you can invoke those kind of models without requiring any kind of consciousness on the part of the model. Likewise, machine learning is very much an unconscious process. Even the kind of state-of-the-art machine learning based on deep neural networks, nobody would claim that the machine is in any sense aware of what it's learning, even though some of the most sophisticated deep networks are now actually generating semantic representations of the information. So they are in some sense internally representing the knowledge. If they're doing something like language translation, then they are much more sophisticated than they were 10 years ago. But I don't think anybody would describe to them any degree of consciousness. The issue of the sort of open physical system does run into the usual quantum issues. You can't describe an open physical system by defining the position and momentum of every subatomic particle, because Heidelberg says you can't know them both at once, except within a certain degree of tolerance. I'm sort of I'm not sure I fully tracked the argument that that Mark presented in his talk, but I don't think it is particularly relevant to the kind of work that's currently happening within the Human Brain Project. It is philosophically very interesting, but I do see consciousness as a continuum, and probably by the time you've got to a grain of sand, you're indistinguishable from the asymptote of zero. So I think I'll stop there and throw it open to the audience.
Yes, thank you very much, Steve. I would like to give Mark a possibility to respond.
Thanks. Where should we start? Firstly, I don't think it's too important in the development of the reductio to get hung up that I happen to choose the positional momentum as parameters I would model in my state description of the rock. It could be anything. I just happen to pick them. After we're just using a way. All we're doing in this move of the argument is finding some way to characterize at intervals what the subatomic particles are doing, and the key claim is that the patterns or the states that the rock or the cup of tea will transit over in a finite time window is a non-repeating sequence of states. That's the important thing. What particular things I choose to parameterize is pretty well irrelevant. So I'm not sure that the quantum objection, if you want to give it that name, really holds. And the second point that Steve alluded to is the importance of stochasticity, or in a loose sense, non-determinism. The idea that some people are very interested in stochastic automata. Well, if I can just move my slides on a little.
Wait, I'll just change something so you can put the slides back on.
Oops. Right. Well, one of the reviewers of the paper that I wrote outlining this argument made a very similar objection. I call it the stochastic machines objection. Basically, the dancing with pixies reductio ad absurdum particularly targets discrete state machines. On the surface, there's nothing to say about a computative conscious state of a stochastic automaton. What we mean by that, in a stochastic finite state automata, the future state of the machine is determined by a probability distribution which determines, given the current state and any input, the probability of entering any future state. If the stochastic element is generated by a genuine stochastic source, for example, shot noise, then although in one sense conceding that computations alone are not necessary or sufficient for consciousness, it would seem that the objection is uncontroversially true. However, the probability distribution of any genuine stochastic source, such as shot noise, can easily be simulated to any specific degree of accuracy. The behavior of the two programs, one whose state evolution is determined by genuine shot noise and the other by a simulation of that shot noise, from the outside would be indistinguishable. Hence, for the stochastic objection to hold, we must insist upon some unknown and ill-defined properties of genuine random numbers, as opposed to computationally simulated random numbers. Further, if the stochastic automaton obtains its genuine random numbers by, say, reading from a latch at a specified address, we could replace the genuine stochastic numbers by computationally generated ones, and the machine's behavior would be indistinguishable. However, only in the latter case. However, in the latter case, ex hypothesized consciousness would be absent. Thus, for the stochastic objection to hold, consciousness must be defined as a fundamental property of genuine noise, a genuine random source such as shot noise, and not the underlying computations. So the stochastic objection effectively reduces to a claim about the properties of noise vis-a-vis consciousness, and not about the putative phenomenal properties of computations alone. And hence, I suggest is irrelevant to the computation of artificial consciousness project and the dancing with pixies.
Thank you. I think...
one other clarification that I've really chopped down and this presentation quite a lot today. And one thing that I didn't review that I would normally take care to spell out is as Steve alluded to, different types of consciousness, and we might have after that block access consciousness. We might think of phenomenal consciousness, the ineffable red of a rose, or what it feels like to be slapped on the head, for argument's sake. Or we might think of higher order consciousnesses. The type of consciousness to which the Dancing with Pixies reductio targets is primarily phenomenal consciousness. It's a raw sensation, if you like. Stop at that.
Thank you very much, Mark, for this clarification. The chat is overflowing, or like people would really like to ask some questions as well. That's why I'm interrupting you a bit.
Yeah.
So I don't know. Steve would probably also like to respond, and I know that Dave Lester has been holding on.
Genau. Und hast du ein 3-5 Klinke dann?
Dave Lester, would you like to ask your question?
Okay, so the first thing that I observed here was that Mark seems to have made the transition to a discretized time, in which case his finite state automata model is fine and dandy. The problem I have is that the transition from what are effectively computable reals to the discrete values is just not a computable function. And so we really need to distinguish here between whether we're talking about the countable set of computable reals as the input, or the rational countable set of rationals, or for time this is, or for voltage, because fundamentally you can't do the threshold determination accurately as you would wish in order to determine whether you've got a 0 or a 1. There's always some indeterminacy lurking when we make the transition from what I would call a continuous or mixed or hybrid system to a fully discretized version, such as the sort of thing we typically run as a computer program. So I'm curious where Mark sees the transition there. What is his modeling assumption for the real world that he's modeling? I think that makes a critical difference to the argument he's making.
I'm trying to think whether I've got some slides on this objection, but to save me having a look, I'll just try and give you a response without reference to those. The key point, the key target of this reductio is the classical machine consciousness paradigm that a suitably programmed machine will bring forth phenomenal consciousness as it executes on some input. That's the target, if you like, that I'm addressing. Now, if we want to move on to looking at particular properties of reals or continuous inputs to our system, that's a separate issue. As it happens, I believe that I can extend the Dancing with Pixies reductio via the Nyquist-Shannon sampling criteria to cope quite adequately with the continuous real world. But for the moment, let's bracket that in a Heideggerian sense and put that to one side and just keep it in the simple case when we're dealing with a very digitized world. The question is, does the argument hold? Well, everybody I've spoken to in the machine consciousness community, and I've spoken to quite a few over the years I've been presenting this reductio, is quite comfortable with the idea that, in fact, for example, Igor Alexander is a classic, is someone whose work I might address now. Igor's developed a neural network simulator called Magnus, which we can run either in hardware or we can run in a virtual simulation. Now, the claim is when Magnus transits certain states, there is something it is like to be Magnus simulator. That's the strong claim. The point is that the Magnus system is completely a software system. It's a virtual neural network simulator existing in a virtual world. So for the Magnus case, then everything is digitized from the get-go, if you like. And I can trivially run the Dancing with Pixies argument to show that if there's anything that it's like to be Magnus as it executes its programs, then such phenomenal consciousness lurks in any open physical system.
Sure.
as I said, I think we can do it with the real world. The stepping stone I used towards the real world in a normal robot system was to use the University of Reading 7 dwarf robots, which sample their world at a particular frequency, in that case, 50 times a second. Now, the claim is from the group that designed those robots, particularly Kevin Warwick, was that over a finite time period, there was something it was like to be one one of those robots as it zoomed around its corral. Now, each of those robots samples the world and gets some input from that world. I just suggested, right, imagine logging that input. So I now have however many seconds of data logged information. And I can then just use that information to map that contingent counterfactual finite state automata back into a simple linear inputless finite state automata, and then run the Putnam mapping and find that consciousness anywhere. So I've taken two places there: the real robot in the real world, the Snow White and the 7 dwarf robot, and showed how the Dancing with Pixies reductio holds there. And I've also taken a slightly more abstract form of the argument when we're looking at a robot simulator, if you like, a virtual robot working in a virtual world, and showed again how we can trivially run the Dancing with Pixies reductio. If you then want to make a particular point about consciousness being in some sense intimately linked to the reals and to the continuum, then as I said, I think we can also begin to make those. And frustratingly, I haven't got with me the slide to illustrate this, but if my claim, the claim I want to run is if we sample appropriately fast, as defined by the Nyquist-Shannon criteria, then again we can run the Dancing with Pixies reductio on that sampled data.
Yeah, I'm suggesting that this is where your introduction of non-determinism is coming in. That this transition point between continuous and discrete is actually the. I mean, Steve and I have batted this around for a long time, and it's fundamental to the analog electronics.
Sorry, the line is breaking up. I can't hear. Can you take the question?
I was saying, I believe that's where your non-determinism is coming in. It's coming in as a result of the transition from the continuum to a discrete space. Mm-hmm. I'm curious to know whether that affects the argument. If we add a non-deterministic element into this, does that?
I tried to discuss that. Did you not find that those 3 slides convincing? I presume you didn't.
I came in about 10 minutes late, I'm afraid.
Because I particularly addressed that. Perhaps we can take that offline if anyone else has got a question. If they haven't, I'm happy to talk about it now.
Yes, Mark, you're right. There is actually one more question, I think, from Christina Aikadi. Christine, please ask your question.
Okay, can you hear me?
I can.
Yeah, okay. I was coming at this from a much more social science angle, and the question was both to Steve Furber and to Mark. Because as Steve said, it's entirely possible to have a conversation about machine learning and cognitive computing without talking about machine consciousness. But we are inundated in the general press, and journalists are all talking about, and a lot of speculative ethicists are talking about the singularity. I was wondering whether you think that there may be strategically, politically usefulness for some to distract the public attention from immediate issue that relates to machine learning and cognitive computing today, by focusing fears and worries to a kind of hypothetical future occurrence, like something like there is nothing to worry about until the singularity is here, and just don't worry for now. Yeah, that's some kind of question.
Okay. Steve, do you mind if I kick in first, or do you want to go first?
Well, I mean, my comment is very simple. I'm a singularity skeptic. I think it's based on a fallacious model of intelligence.
Well, I'm a singularity skeptic too. I think that that partly follows from the presentation I made today. I think the singularity would be true if all aspects of human mentality were instantiable by a suitable computer program. But I've tried to show today that certainly phenomenal consciousness, if that is instantiable by a computer program, then the very notion of consciousness becomes vacuous because we find it everywhere. Panpsychism is true. And therefore, I hope that this reductio ad absurdum argument leads us to reject the first horn of the argument, and that is that the execution of a computer program is sufficient to bring forth consciousness. So if that's true, if I'm correct, then no computer program, the execution of no computer program will ever bring forth a phenomenally conscious state. So that's one point. I've also published widely and I'm very interested in John Searle's Chinese room argument. And if Searle is correct, and my own intuition is that he is, then again, the execution of no computer program is sufficient to bring forth genuine understanding. And then an issue that Steve raised, for which he's clearly he's a skeptic, but again, I sit probably on a different side of the fence here, is that of Roger Penrose. And Penrose suggested that there was something about mathematical understanding which is fundamentally non-computable. And my own intuition, having studied Penrose's work reasonably in depth, is that I think that he might be correct there. But my point, to drive home the point, only one of those three examples needs to hold for there to be a difference between what we can do computationally and what real minds, what real people, what real societies can do. So if that's the case, that there's a gap between what computers can do and what humans can do, then it doesn't seem to me that the singularity will necessarily or ever be reached, because it will always be the case that a human plus a computer will always be better than just a computer on its own. It will never be a case where we get this runaway danger of a super intelligence coming forth to dominate and subjugate mankind in the kind of visions that Ray Kurzweil and Stephen Hawking have been trying to push recently. So yeah, I'm a skeptic on the singularity. I think it's a not well-defined notion.
Yeah, I'm a skeptic too, but I'm wondering who is it useful for to bring it up so much while absolutely ignoring other issues that are pertaining to today's stupid cognitive computing.
Well, I totally agree, and in fact, as a paper in the new volume by Vincent Muller on the existential risks of artificial intelligence that I've contributed, where I make the case that I'm extremely concerned about the dangers of current AI systems, or what I call artificially stupid systems, in the context of autonomous weapons systems. That's hence my involvement with ICRAC, the International Campaign for Robot Arms Control, because it seems to me that there are real dangers once we start letting loose autonomous systems and arming them with weapons that can kill humans. And we really ought to be thinking not once, not twice, but 100 times before we unleash these systems on an unsuspecting world.
I did make this point this morning, Mark, but we've had autonomous weapons for a very long time. The landmine is an example.
The landmine's banned, though. What we're trying to do at ICRAC is get autonomous weapons covered by the same.
The landmine being banned, but there are still an awful lot of them around.
Yeah, but there's an international prohibition on their deployment, which is what we're trying to get of autonomous weapons with ICRAC. Obviously, the research that goes into autonomous systems is going to continue whatever the UN happened to say, and I'm very glad that it does. But I've been for a prohibition on their deployment and use. And I think there are very good reasons to think about that. I think there genuinely are existential risks of having autonomous weapons systems let loose on the world. And I'm happy to talk about that ad nauseam, given the platform.
Okay, Mark, Bishop Steve Furber, thank you so much for your presentation and commentation and the discussion. I think it's been extremely interesting. I hope for you as well and for us as the audience. We will continue now.